All right, hello. My name is Andrew Lamb. I'm a staff engineer at Flux Data, and I want to talk to you about using sorting in database systems, specifically some common techniques that are used uh, to take advantage of sortedness. This is in the context of a query processing seminar I attended last week, where we were discussing how to do query processing and stream processing and how sorting was related. And this was meant to sort of give people some ideas of what's possible. I basically wanted to describe three levels of techniques. The first is when the data is fully sorted. Then when the data is partially sorted, I'll explain what that means as typically a prefix of the sort order. And then I want to talk about some work we've been doing recently about when the data is almost sorted. So it's not uh, completely sorted, but still taking advantage of that. And I'll also touch a little bit on the analysis required to take advantage of this sortedness. I should basically say not everyone, by the way, likes to use sortedness. Because it's harder to parallelize, but there's certainly plenty of work in the sorting uh, in the database literature about sorting. Um, in particular, this is classic. I think it's from '91, maybe from Goetz Graph that talks about. Oh no, 2006. I'm sorry. That talks about how to implement database sorting in databases. If you ever want to learn about how you should sort large amounts of data and what the techniques are, this is the paper to read. It's both a survey and it outlines all the techniques, but it really focuses on how to get the data sorted. It doesn't really describe what to do with it once it is sorted. There have been known basically even since the earliest of the database days, like the Salinger paper from System R actually describes interesting orders. So even 50 years ago, well, it's close to 60 years ago now, I guess. Um, People understood that, or 50 years ago, people understood that taking advantage that if the data was sorted, you could take advantage of it. But I don't think I'd ever seen sort of a concise description of how to take care of it. So my personal conjecture is that sorting is really important for analytics because of the high data volume, and in particular, that makes secondary indexes like B trees, which really are, if you think about it, just a subset of data sorted in some different way. And a bunch of other indexes have that property. So it basically makes the cost of secondary indexes very high because you basically have to store an entire new copy of the data and you also have to maintain it. And then also you have to be clever enough to use the index when necessary. So what that means, I think, is that if you're going to take advantage of sortedness, specifically in analytic systems, you really need to typically sort the primary data. And there's all sorts of ways to assess the primary storage. And you can either pick a subset of columns, you can try to do sort of higher order clustering like Z ordering or liquid clustering, I think are some common techniques, but you really aren't sort of guaranteed to get the data in the order that you want because sorting is really expensive and you have to pick one order. Right? So you don't necessarily get to have multiple different sort orders, you get to only pick one. So anyway, the point is sorting is important and especially in analytic systems. So let's go into now how to take advantage of that. So in this case, let's talk about fully sorted data. This is like the classic simple example, right? If your data is all sorted, I'm going to use time series data in all of these examples. Probably that's because I work for a time series company, a time series database company, Influx, but all these techniques apply to any sort of data. It's not just time series, although time series offers very good examples. So in this case, if you've got data that's sorted by time and you wanted to do a query based on time, right? Like you wanted all the data between 12 and 12:05, it's actually very straightforward to do a binary search to find the two parts of the input that correspond to those ranges. And since you know the data is sorted, any rows that are outside this range can't match the predicate, and so you can just return. So it's like clearly, if you have data sorted, you can find what you want more quickly with binary search. That's one simple example. The next simple example, which may be even so obvious people don't even think about it, but if you have the data pre-sorted, example by time, and the query then asks for data ordered by time, you don't have to do any extra work. You can literally just read the data out in order and you can answer the query. Now, I think it's kind of interesting, without any extra work, especially when you have to sort large amounts of data, not having to sort can save a large amount of time. It's also kind of cool that this works for monotonic functions as well. So if the data is sorted by time, the query doesn't ask for order by time, but instead it asks for order by, for example, date shrunk by hour. So you chop off the minutes and seconds and anything smaller. This data is actually still sorted by that expression. So you can take advantage of sortedness even if it doesn't exactly match the order by clause. But of course, it matters exactly what that function is matters. And we'll talk a little bit more about that later in the talk. But Again, this it's already looking like this is pretty useful. Another example is top K. This top K queries is like the database implementation detail. That's what top K is. But the queries basically are ordered by within the limit of something. Right? So you're finding the top n values where n or k, I guess, sometimes. And often there's a special operator database systems that do that find order by plus limit. In this case, however, you can actually look interestingly if your data is already sorted by the time, the column in question, in this case time, and you only want three, again, it should be pretty straightforward, pretty obvious. You can just read the first three columns, and that is your answer. You don't have to do any additional processing, or which can be very fast if your data set is large, right? Okay. Now let's move on to something slightly more interesting, and maybe slightly less obvious. So, in particular, if you're going to do aggregation. So typical aggregation in a database system requires, aggregation. You're basically finding all the rows that have that have the same grouping key. Then you compute the aggregate across all those rows and emit one row per grouping key. So now, if you can guarantee that your input is contiguous, such that all the values for a particular grouping key are next to each other in the input, you basically know as soon as you see a new grouping key, uh, you can emit what you've currently buffered. And so that turns what sometimes become like you basically have to build all the groups in memory and then emit them. So that's both a pipeline blocker in the sense that you can't start producing output until you've seen all the input, but also it can potentially require large amounts of memory because you have to buffer the entire input, right? But now you buffered the entire, basically of every group. So you don't actually have to buffer the whole input. You have to buffer enough for one individual group, but that's it. So in this case, however, I'm talking about if the data, if the input stream is organized such that once you see a new grouping value that you're never going to see the previous one again. That sounds a lot like sorted, right? So basically, if the data is sorted by the grouping keys, you can use special operators that don't have to. They both don't have to store all the groups in memory, and they can emit immediately once they see new groups. So they can stream out. They can start streaming output very fast, and their memory requirements are much lower. So those are typically called streaming or non-blocking aggregation operators. In this example, if we're grouping by time and city, you see I have clearly ordered this data by time and city, unsurprisingly. What the system can do is it starts scanning down the rows and it finds the first, it basically computes the average, which is the aggregate that's requested for this query of the temperature until it finds the next row that basically where the sorted key doesn't match because that now corresponds to a new group. So once the first time it sees that, because it knows the data is in sorted order, it's never going to see rows with 12 o'clock in Boston again. So they're not going to emit the current average and reset the state. Right? So you can just emit that row and then carry on scanning the rest of your data like that. So again, for some systems, especially ones that are streaming or ones that you're trying to, not have to buffer all the groups in RAM, this can be very effective. A very similar optimization and implementation may happen for window functions. For those of you who might or might not remember window functions, they are similar to aggregations, but but they don't actually reduce the cardinality. They basically, for every row, it gets put into a partition with the partition by clause, and then within that partition, the set of rows gets ordered, and then within the row, every row, there's a window function that gets run that can look at values before and after. So typically, the way these get implemented is you'll partition the data by, well, you'll actually sort the data first by the partition by columns and then by the order by columns. So they all are now clustered together. So each window basically is contiguous in the input stream. And then once you have that, you can actually then just stream the data as it's already ordered through your window operator. And as the values are computed, you can emit them directly. Does that make sense? In this case, right, we're partitioning by region, order by time. So you take, because the data is sorted by region and time, you actually know that that window is contiguous, and you can just basically compute the window functions directly. Once you see a different change in the region, you can emit the currently computed window functions directly. So again, maybe obvious, but having that sort of information really helps. All right, another thing you do is do the same thing with joins. Right? This is the classic merge join operation. Sometimes systems will actually even sort the inputs so that they have this property. But the idea here is that you have the data that's sorted, both relations, right? Joins are joining two relations together, two tables. The two inputs have to be ordered by the join keys when you're doing an equijoin. So in this case, you're joining. I guess this would be the lookup table. This is the sensor readings, and you're joining using the sensor ID. And you can see the data is actually ordered by sensor ID in both cases. And so the way a merge join works, it leverages the fact that the data is sorted by keys. And so you just scan down both relations with the current join key until you reach rows that have different join keys. Right. Now, once you've reached that, all the rows that in the previous one, the rows with S1 as a join key, you can now match them, do the join, maybe depending on what kind of join it is, you'll omit it, maybe it's outer joins, whatever. But basically, you're able to omit and then continue on. And so unlike a hash join, for example, this technique allows you to both omit rows after, like as soon as data starts flowing through the plan, as soon as you find matches, and it does not require buffering, aka hashing a large number of join keys. All right. So that's what you do when the data is fully sorted. Now, what can you do when the data is partially sorted? And what do I mean by partially sorted? We got to explain that first. Partially sort, at least how I'm going to describe it, really means sorted by a prefix of the desired sort key. Right? So if you really wanted so here's two examples, right? On the left, it's ordered by time and then city. So in time, right? So these values are ordered by time. And then for rows that have ties in time, so like 11 o'clock, there's actually three distinct cities with the same time. And in this case, they're ordered ascending as well. Right, so this is the full sort order. It says both time and city. And then on the right-hand side, you have a partial sort where it's only ordered by time. So in this case, you still got all the 11s at the top, but in this case, the cities might not be in any particular order. And so the question is, can we take advantage of this still, right? This data is sorted. Can we take advantage of that partial sortedness, even if it might not be as nice as if it was sorted completely? And of course, the answer is yes, because I've set it up that way. So let's talk about how to do it. The first thing you do is to do, again, there's a variant of the streaming non-blocking sorting. In this case, you can't emit rows immediately once you see a change in the prefix. However, what you can do in this case, for example, if the data is only ordered by time, right? You can see it's ordered by time here at 12 o'clock, but these aren't ordered. The cities aren't ordered. And the query wants ordered by time and city. What you can do, again, is you scan down and find where the prefix, like basically where the sort order key, where the sort key changes. You can't emit those rows directly because they're not actually sorted the right way, but you can sort now in memory or whatever your favorite technique is from Gutz's paper. You can sort those three rows and then emit them, and then clear the memory and then move on to the next. Right, so because we found a new time, and so then basically you can buffer these rows. You do have to sort them, right? So this potentially requires some non-trivial amount of memory, depending on how many rows there were that had the time of 12 o'clock. But at least you don't have to sort the entire relation, right? Because it's already partially sorted. You can just sort the unique keys and emit them. So that again reduces overall memory requirements because you don't have to sort the entire relation, and it can produce rows much quicker rather than have to wait for all the input before you start producing output. You can produce output immediately. So maybe overall, query throughput or something like the number of rows output, how long it takes to output all the output might not change, but the amount of time required to see the first row could drop dramatically. All right. Next thing I want to talk about is partial sorting and aggregation. Again, this is very similar to the sorting one. In this case, if the data sort the sort order is a prefix of the grouping keys, you can omit the aggregate again when the prefix changes. Now, it's not again. It's approximately the same general idea. So in this case, again, the data is ordered by time, but not city, right? Ordered by time, and I'm trying to do, in this case, find the average temperature grouped by time and city. So in this case, you can again start sorting, scanning down the input relation. In this case, find all the rows that have 12 o'clock. Once you hit a new value in your order by key, nothing's ever going to have 12 o'clock again. And up here, of course, you have to somehow aggregate this probably with a hash table, a running hash table or something, that you do keep the individual groups around, for the city, although they all have the same time, so you don't have to store that waste space in your hash table for that. You do have to basically build aggregates individually for the distinct cities and then emit them. And again, once you find the new row, you can then emit the output. And so, you know, what this means in practice is you typically will have a hash join or rather a hash aggregator, an operator, something like that. You'll scan the inputs, build up the hash table, build the aggregates in the hash table like normal, except then once you see the prefix change, you effectively emit the hash table, clear it, and begin again. Right? So in that way, you don't build up some massive hash table over the course of the input. You keep it relatively small, and you're able to flush data out as the query proceeds. So you don't have to wait for it to see all the input. Uh, Window functions and joins are basically the same story. Excuse me, I won't go through them again, but they're basically the same general pattern, right? You have to buffer more than you did in the fully ordered case, but you don't have to buffer the entire input. So that's better. No, what kind of analysis you need to support this type of operation? I've just kind of blindly saying, well, if you need the data sorted this way and you have the data sorted this way, how can you take advantage of it? In order to take advantage of it, typically optimizers will track equivalent orderings. So they'll basically track throughout the plan, typically starting from the bottom where maybe the input sorted or whatnot, and then as the data flows up through the plan, they remember whether or not it's ordered or not. Data Fusion uses something called equivalence properties. We have a blog post about this if you want to read this. This is a relatively common concept in any system that can leverage joint order, or leverage ordering in general. And just to give you a sense of what it means, what it typically looks like is that you represent the output ordering of every particular operator, and then you have rules that, depending on the operator and the contents of them, uh, sort of given how the input was ordered, it'll compute how the output was ordered, and then you basically apply that path up the tree. So in this case, if the output order was time followed by city, so the data is ordered by time and city out of the scan, maybe that's how the file was ordered. And then in this case, we're going to project a date trunk. So we're basically going to evaluate date trunk on hour and time. This is the example from earlier. The expression analysis will have to track that the output order is actually now date trunk and city, date trunk hour, blah, 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 but then city. And so how does it do that? So basically, you can't just track columns. You have to also track expressions, and you have to be careful what kind of expressions. This is what I'm going to talk about. I mentioned this earlier. Monotonic expressions basically preserve order. There's probably a more sophisticated concept for that. But in this case, the monotonic expressions are preserving order so that and I'll give you some examples. So here I've got data that's sorted by both by time and then it's sorted by time and then city perhaps. Well, I guess there's no ties. So it's sorted by time and city. And so if you now look at what date trunk hour time is, this would just remove the minute portion of the timestamps to truncate them to the hour boundary. And then you can kind of see in this example that the times are in fact still ordered, even though they've been transformed by this function. However, there's other functions. For example, if you extracted the minute field from time, which is another function in SQL, 58, 58, 59, 0, 1, that's what you get. Now you can see this column is not ordered. So the optimizer has to be clever enough to know that if you're extracting data, or you're calling this extract function, that doesn't pass through an expression, but date trunk does. Right? Okay. Another interesting equivalent analysis expression you can do is something called constant expressions. So in this case, which is actually fairly common in database systems, this is sort of a more general concept when you have a functional dependency, and I'll talk about the special case of constant expressions. But if you got a constant expression, so for example, you have a filter that says I only want the rows where time is equal to 1205. Well, if you know the input was sorted by time and then city, after this filter, you know that all the rows have the same value of time. So because of that, the actual output order is known. You can it'll either match a query that needs ordered by time city, or in fact, if the data wants ordered by city or time, city time, or just a prefix of them. So hopefully that makes sense because time has only a single value, you can move it around arbitrarily in the sort order. And again, since equality predicates are quite common in SQL, this does happen more than you might imagine. And similarly, if you run it through join, it's a little more complicated, but it's very similar. So if you're merging join together, uh, and the inputs were sorted on the key, as long as of course this relies on the particular implementation details of the merge join, but you run them through the different most merge joins will preserve the order. So in this case of data fusion, if we knew the inputs started on the left sorted by L sensor ID and the right started on R sensor ID and then also time, you merge join them all together, the output of that's actually sorted on both left sensor ID, right sensor ID, and time. Or you can, because you know these rows or these columns are equal, you can actually swap them around in the output ordering. So there's these two equivalent orderings that come out of there. That makes sense. So we're basically using the property of the plan as a, we go up. So we start at the bottom. We just use the um, properties of each individual operator to compute the output ordering at there. All right. So that just gives you a taste of like what types of analysis you need to handle this. And now finally, I'm going to move on to almost sorted data, right? So what I mean by almost sorted data, well, almost sorted data is data that's like kind of sorted, but it's not exactly sorted. And this is super common in time series uh, use cases and other places as well, where the input order is often correlated, but not guaranteed to be the same as the timestamp order. So imagine you're like observing something, you're like have a sensor and you're getting readings in. Most of the time, the next reading that you get from a sensor is going to be like later in time, right? So if you think about that, that means the arrival order in your system it's close to the actual timestamp value. Now, in this particular example, I purposely made it so that there's a couple of rows that are out of order, right? So here you got 0, 1, 3, then 2, then 4. So that happens in the real world, but there you can see there's definitely ordering in this column. And now I wanted to talk about a few ways that systems leverage. It is still kind of sorted, even though it's not exactly sorted. So the techniques I just talked about don't directly apply, but we still have some other tools in our toolkit. The first thing you can do is data skipping. This really relies on clustering around uh, it's really a mechanism for clustering, but since ordering and clustering are very related, like if data is ordered, it's also clustered. So if it's partially sorted, it's actually partially clustered as well, mostly clustered. So the way pruning typically works is you have min-max values for files, and then you divide the data up into multiple files based off probably some partitioning key. So in this case, you can see I've kind of taken every hour gets its own file, and then each file stores sort of the minimum maximum timestamp value for that file. And then what we'll do is we'll use an analysis to figure out which one of those files we actually have to skip. So in this case, the query has a predicate between 12 and 1205. So what the database system will do is it will then compare that expression to the minimum maximum values in the different files, and it can decide that certain files can't possibly have values that match that row. So for example, if you know that the minimum maximum value, again, because it's sorted, right, or mostly sorted, the minimum maximum value here is 11 to 1159, it can't possibly have values between 12 and 1205. And likewise, anything from 1 to 159 can't possibly have values in that range, so you can skip reading the file entirely. And this one, 12 to 1259, that one does contain, might contain the values, so you have to look at that some more. But that's already pretty good. We got rid of 2/3 of our files without doing a whole lot of work. Now, in order to actually implement that pruning, the way it typically works is you have some sort of range analysis where the input ranges, the input ranges like the min max values for particular columns, and you have some arbitrary expression, and you're computing the output range. And for Boolean, the output range, if you can pin it to what either true or false, actually, as long as it doesn't pin to, if you know for sure it's always not true, okay, false or null, then you can skip the file. But that's a little bit more. I'm going to show you the way data fusion does it. This is not the most general way of doing pruning. However, it is very fast on large numbers of files. And it's how data fusion's pruning predicate works. You can read about that in the document that's listed below. So in this case, if you have multiple files, as these are the same files as before, right? File 1, 2, 3, and then you know the minimum and maximum values for each for the time column in those files. what data fusion will actually do is it'll rewrite a predicate like this, time between 12 and 1205. It'll rewrite it to the max is greater than 12 and the min is less than 1205. So basically, it's going to rewrite this predicate into an expression in terms of the minimum maximum values on the columns, and then it's going to evaluate this thing with the fast data fusion executor, which the expression evaluator, which is very fast, and will quickly tell you whether this thing's true or not. So, and basically, if this expression is not true, it means you can't possibly evaluate the file. So yeah, like we'll rewrite it using the min max ranges as I just said. Then we evaluate using this sort of synthetic table that I drew over here. And if the expression is not true, you have to scan the file. You don't have to scan the file. So in this case, you evaluate here. You'll find that that expression is false, so it can't possibly be true. That one, middle one, file two is not, the prune is not true, so not false, so you keep it, and the other one is false. So it's just the same answer as before, but I'm just trying to give you a sense of the analysis that was needed to drive that. And the final thing I want to talk about is dynamic filtering, which is actually kind of cool. It's a neat thing we've been working on in Data Fusion, but it's not something that we invented in Data Fusion. It has a long history. Apparently, Goetz invented it. If you read, there was a paper uh, in BLDB that basically cites some of Goetz's early work, but basically the same idea of this sort of self-sharpening query. There's several interesting papers about this, but it's basically high level. So the idea is, I'll give you the motivating example. So in this case, you select star from weather ordered by time limit 3. So what does that mean? That means I basically want the top the 3 rows from the weather table that have the most recent time, which is a very common time series query, right? I just want the most recent values. Now, normal um, databases, even with the top K operator, have this special operator that does both order by and limit in one go, like I was mentioning earlier in the talk. And the way they typically work is they have a heap and they keep track of the 3 most basically highest values. So you'd scan the table, you'd keep track of whatever the top 3 were that you'd currently seen, you'd update that as new rows flow in, and then emit it. However, this is not great, right? Because in this particular case, especially for a column store, you are evaluating all of the columns. So basically, you're doing a lot of work to decode this highly encoded and compressed data in column form, run it through this top K, keep only the top 3. Right? So you basically scanning the entire table, could be millions and millions of rows, to throw away everything except only 3 values. So the question is, can we do better than this? Of course, the answer is yes. Otherwise, I wouldn't be talking to you here. And the way it works is we add this special filter. And we're going to add a filter that, in this case, it has the form time is less than some value. And as the query runs, and as this heap gets updated, we're going to basically pass information down about the current heap min to the filter. So if you think about this is like the optimizer sticks this filter, but we don't necessarily know what the values are here until you start running the plan. So this is like some sort of, we call it dynamic filter because it gets updated during execution. I believe there was the paper called PolarDB that talks about this optimization as a self-sharpening filter, but it's the same idea, right? As you gain information in another part of the plan, you effectively create a filter that gets better and better based off that information. We do this, by the way, also for joins, for sideways information passing, but I don't have that in this talk. So now the question is, so this is this dynamic filter. Now, how does this relate to the partially ordered data that I was just talking about? So let me start with an example where there's no sortedness in the data of how this works. I think it'll become easier when then I'll show you what it works like when it has sorted data and how that affects it. You can see here the as execution time goes over, we're going to run the same query I was talking about before, right? Select star from weather, order by time limit 3. Here's an example of a table like that. It's not ordered. It has values all over the place. So when you start, you don't know what this filter is, so you basically have to scan all the rows. So let's imagine you're scanning in 4 row chunks, four row batches. So we get the first 4 rows, and we feed them through the top K heap, and the top 3 rows, which are basically the lowest 3 values, the 2, 4, and 7, 1102, 1104, 1107, right? Those go into the heap, and actually now, given that information, we actually know if any value is less than 1107, it can't possibly appear in the it won't be one of the top three values in the top K heap, right? Because we already know that we have three values that are 1107 or less. You understand how that works? So we have this filter. So now we already basically can induce this filter here after reading just four rows. Now you read the next four rows, and I tried to highlight here because we knew that we already had three values that were less than 1107, or we can immediately prune out 1110, right? Like we didn't have to read that; we just filter that out. And then in this case, we've got 1101, 1103, 1100. After this second block, we now know that the heap has the top three values are currently 11, 1101, and 1102. And so this is actually, we can update the filter because now the greatest value in the heap is 1102, so we can scan anything less than that. And it actually turns out in this example, the rest of the rows actually can get all skipped because nothing in there was greater than 1102. And so you can see, right, as you find the contents of the heap, the filter gets better and better. And so what you can so consequently, if you know your data is already kind of mostly sorted, even if it's not exactly sorted, you can play games, right? As long as you basically, if you think about this filter getting more and more exact over the course of the query, it gets exact as it sees the rows that are lower. So what you really want to do to make this filter really effective is you want to make sure it sees the actual top three values as soon as possible in the plan. And so if you know your data is partially, almost sorted, you can actually reorder the data so that the most likely rows to match, basically to be in the top K, are seen first. Then that filter technique will be much more effective. So here's an example with the other one where this data is now mostly sorted. This is the same mostly sorted example or almost sorted example from before. Again, you start with an empty filter in a top K. This time I'm going to read the top three values. And actually, even though these aren't sorted, they do contain the top three values entirely. Right. So because it's almost sorted already, this dynamic filtering effect is actually very, very effective. Then you can just see we're going to basically prune out the whole rest of the file without even looking at it. And you can, so in this case, I'm showing sort of row level filtering, but these dynamic filters can be used for file pruning too. So in fact, Data Fusion, once you've looked at a file, the next time it goes to open a file, if the filter's gotten better, this dynamic filter will actually prune those files out as well. So as long as you arrange to see the top K in the first file, you could probably, once you found it, prune out everything else in the other files, prune out all the other files and skip them entirely. So that's my talk. Hopefully that was interesting. Give you some idea of how you can leverage sortedness in analytic systems. None of this stuff, I think I certainly didn't invent it, nor did Data Fusion. It's been floating around in various systems for many years, but I think it was interesting to kind of bring it all together into a single talk. I also think there's a clear connection between the sortedness and streaming that I certainly didn't fully appreciate until I started working on Data Fusion. And of course, you have to have a non-trivial amount of analysis in your database and database optimizer to be able to take advantage of these things. So with that, thank you very much. I hope you enjoyed